Good morning, everyone, and welcome to this Thursday morning session or Zoom session. And thanks for making the time. And I see we've got a really good audience, so we'll have lots of good questions and discussion lined up with Lew Ashwal. Lew did his PhD at Princeton University in 1979. And from 1979 to 1981, he was a postdoc at the NASA Johnson Space Center in Houston. From there, he became a staff scientist at the Lunar and Planetary Institute. In 1990, he moved across to South Africa, and I think that was sort of helped or initiated by his close friend, the late Martin de Wit. Sadly, Martin's no longer with us, but that's how Lew got here, where he became a professor at RAU, Rand Afrikaans University, which is now University of Johannesburg. And since 2001, he's been a professor at Wits University. He has wide-ranging interests in petrology, mineralogy, geochemistry, tectonics, geodynamics, and meteorites. So thanks, Lew, for making yourself available, and we really look forward to your presentation today about a study and a subject that's close to the hearts of many of us.
Man, thanks very much, John, for the introduction and also for the invitation to present this stuff to a group that I normally wouldn't have much interaction with. So I thank you for that. Okay, so my talk today is going to focus on the 4 Southern African large igneous provinces that are spatially overlapping and intruded and extruded pretty much on top of one another over the course of about 2.5 billion years. My interest in this subject comes from my interest in figuring out where these magmas came from, and specifically the mafic magmas. So I'm interested in the mantle sources and the evolution of mafic magmas. This can be illustrated very nicely in South Africa, where we have these dolerite sills. So this is the Karoo large igneous province, and these dolerite sills are all over the place. They're everywhere. And so here we have probably the representatives of 2, maybe 3 million cubic kilometers of basaltic magmas that were placed into and onto the Kapval and Zimbabwe cratons about 182 million years ago. So the talk won't say very much, for better or worse, about the crustal magmas like the rhyolites and dacites and granitoids that are commonly associated with these kinds of provinces. Now, there's a huge literature on large igneous provinces, including these 3 books. And on the left side of this picture shows you the most recent one of these by Ernst in '97. And it's Ernst who actually provides the definition for what a large igneous province must be. And according to him, the areal extent must be bigger than 100,000 square kilometers, with a volume of more than 100,000 cubic kilometers, and a magmatic lifespan of less than 50 million years. But I and my friends have a suspicion that most large igneous provinces are much bigger than this, and are emplaced at a much a smaller period of time. And we suspect that the reason he defined them in this way is so that he could allow the Inclusive River basalts of the Western USA as a large igneous province. I'm not sure that that's too fair, but what we're talking about mainly in the Earth is areal extents of 1 million or more square kilometers and volumes of at least 1 million, and sometimes very much more than 1 million square kilometers. Now, these large igneous provinces really are nicely described as flood basalts, and in fact we could say they're flash flood basalts because their magmatic lifespan is so short. They occur in a very short amount of time. typically a few million years or less. So here's some pictures of the products of large igneous provinces. So here's the very well-known Deccan of India, showing the stratigraphic successions of mafic lavas, basaltic lavas. And here's also in the Deccan is a dolerite dike, about 20 kilometers long. And I remembered in putting this talk together that a few people who know that I have been to India about a dozen times asked me, did I ever go and see the Deccan? And I say, my answer is, well, unfortunately not. I didn't really was interested in other things besides the Deccan until my friend Sharad Master, who was with me on one of my trips to India, he said, no, Lew, don't you remember that we were in a bar in Mumbai and the columns of that bar were composed of vesicular basalts from the Deccan? So it's not true to say that you never saw the Deccan. Not sure that qualifies as really seeing the thing, but you know, Sharad is never wrong. He knows everything, that guy. Okay, so on the top right here is an example of some of the mafic sills, the dolerite sills of the Kondo igneous province, which I will be talking about today a little bit. I did some field work there. In fact, it was my very last field work about a couple of years ago when we went up to visit the Kondo exposures in the Chimanimani mountains of eastern Zimbabwe. That was a great deal of fun. Now, this picture on the lower right shows one of Richard Ernst's favorite things. What he likes to do is define the plume impingement sites, which are shown here as stars. And so what he does is looks for dike swarms and then kind of projects them to a point where he thinks they intersect. And that to him represents the plume impingement site. Well, maybe not, but this is one thing that you can certainly do with plume-related magmatic products. Now, this picture is a remarkable one to me, and it comes from a cute little book called Evolutionary Catastrophes by Vincent Cortiot from Paris. And what he's plotting here is the age of flood basalt, so the ages of large igneous provinces. And on the y-axis is the ages of mass extinctions. And so this is a remarkable correspondence, which to him and to most other people says that there is a causal link between the occurrence of these catastrophic flash flood basalts and mass extinctions. The best known of these, of course, is the Deccan of India, which corresponds to the KT boundary extinctions, during which about 70% of the life forms on Earth were extinguished, including all of the dinosaurs except for the avian ones. And so this is important not only for igneous petrology, but for evolutionary biology. Here's an outline of where this talk is going to go. And so my interest is what are the sources? What are the mantle sources? What are the possible sources? What are the impossible sources for continental large igneous provinces? And here is a cross-section, a schematic cross-section through the Cratonic lithosphere to a depth of maybe 700 or 800 kilometers. And I've listed 1, 2, 3, 4 possible sources for large igneous provinces. So I'll just go through them a little bit. The first one is the SCLM, that's the subcontinental lithospheric mantle. And on the picture, this is shown as this green region here. Another possibility is enriched domains in the SCLM. So I show these as these little blue blobs, sort of a plum pudding idea. Those have been also discussed as possible lip sources. Another one is the convecting asthenosphere, shown in yellow here. And these bright yellow bananas are meant to illustrate the patterns of convection. And then the fourth one is mantle plumes themselves, which is the origin that I favor, and I'll try to outline some of the the thinking and the evidence for this, in at least in terms of the Southern African lips. So all of these have been discussed and proposed at one time or another, exclusively or in various combinations, with or without crustal contamination. So the lips, of course, must traverse through the continental crust, and there is every opportunity there for interaction, assimilation, contamination with components from the continental crust. Now, as I've already said, there's a huge literature on large igneous provinces. There is no consensus whatsoever about what the possible sources are. Many people who have written multiple papers on this subject have changed their minds back and forth over the years. But in reading the most recent literature, it seems to me that you could make a case that support for an SCLM source persists and is growing. And maybe this represents the conventional wisdom these days. I'm not sure, but the purpose of my talk today will be to try to convince you that this is an impossible source for large igneous provinces. I think that large igneous provinces come from below the lithosphere, so somewhere in the asthenosphere or in the mantle plumes themselves. Okay, so let me go through in just a little bit of detail the four overlapping lips of Southern Africa, going from oldest to youngest. And the first one is the Ventersdorp. I don't really need to speak too much about it because we heard a terrific talk last week by Gerhard Menkes, who outlined almost all of the relevant features of Ventersdorp a week ago. So let's just go through the properties here. The age is interesting. The age of Ventersdorp is somewhat of a problem, as we discussed last week. So 20 years ago, Armstrong and his friends published some zircon ages that were about 2.7, 2.71. And then a few years ago, there's a much more recent paper by Ashley Gumsley, in which he said, no, it's actually older than that. It could be as old as 2.8. And that is uncomfortable to a lot of us because it either implies a very long duration for the Ventersdorp, or it implies that there may be more than one lip exposed in the stratigraphy of the Ventersdorp. Gumsley, of course, didn't make any friends whatsoever in Australia because he claims that Richard Armstrong's ages are actually wrong, and so we should discount these. But I think all of this, what it clearly means is that we've got to do more precise dating of Ventersdorp and try to constrain the duration of this magmatism as best as we can. Okay, so the rock types range from komatiitic basalts through to basaltic andesites. I won't talk about the felsic rocks, but there are plenty of those as well. And an important feature of Ventersdorp is the extensive alteration that almost every rock shows. So they're very low-grade altered rocks. Olivine is present, but it's pretty rare. And this is something that you've got to deal with if you're interested in the geochemistry and the isotopes. And we'll see more a little later about where this might lead us. So Ventersdorp is unconformably overlying the Witz supergroup quartzites. And the size is estimated at about 300,000 square kilometers based on rock exposure. So in this map, the darker colored regions are examples of Ventersdorp materials exposed in outcrops. And then there's also zillions of boreholes. And Gerhard last week shared some data for lots of them with us. And then there are also Ventersdorp materials that occur as xenoliths and kimberlites. And so based on these three different types of materials, we can begin to constrain the area in which the Ventersdorp magmatic products occur. And so if you assume a thickness of about 2 or 3 kilometers, it gives you a magmatic volume of about 0.75 million cubic. Of course, there also, we discussed a little bit last week that in Australia, there's the Fortescue group that may be correlative with Ventersdorp. But that is a topic that I don't know very much about. But if you include the Fortescue, it's going to add about another million cubic to the Ventersdorp volume. Okay, the sources for Ventersdorp, and I'm just listing here examples of where our friends and colleagues have proposed an SCLM source for large igneous provinces. So for example, Goonie Marsh likes the SCLM as a mantle source without crustal contamination. There's other papers that reach a similar conclusion, like the work of Kent Condi and some others. Okay, Bushveld. What can I say about the Bushveld? You know, Wits University is a very Bushveldy place. And so I feel like I'm being bludgeoned all the time by staff members and students who talk about various aspects of the Bushveld, and the introduction is always the same. You know, upper zone, main zone, critical zone, Merensky Reef, blah, blah, blah. Come on, we've heard this 100 times, and I'm actually must confess that I'm getting quite sick of listening to these introductory remarks. And when I have to review an honors project or something like that, all I wind up doing in the introduction is changing around a few commas and semicolons and things like this. So we all know about the Bushveld complex. What I can tell you, that may be more interesting, is that there's almost no consensus about really anything to do with the Bushveld complex. So some time ago, I made a list of the things that nobody agrees on. So for example, the continuity between the eastern lobe and the western lobe and the northern lobe and all that. There are some who say that these are separate intrusions. There are others who say that it is continuous, completely across the 400 kilometers between the western and eastern limb. Okay, there's no agreement on the mechanism of emplacement, the number of magma influxes, whether there's one or hundreds, can't agree on that. We don't know whether these influxes represent melts or mushes. We don't know anything with any confidence about the magma compositions. We can't agree about the role of crustal contamination. We don't know the origin of the layering. We don't know the origin of the ore deposits, and we don't know the tectonic setting. So I think it's fair to say that there's only two things that everybody agrees on. One is that the Bushveld is big. This is a monster layered intrusion, probably the biggest one in the solar system that we know about so far. So it's big, everybody agrees about that. And we all agree about the age. And so there's a lot of new high precision zircon work that's being done by a number of groups, Jim Mungall and James Scotes and Armand Zeh. And it looks very much like we can think about the Bushveld as having been emplaced in a time period of less than a few million years, maybe 5 or a lot less. All the rock types we know about, they're all magmatic cumulate rocks, so that means they are they represent various assortments of minerals like pyroxenes, feldspars, to a lesser extent olivine, chromite, magnetite, ilmenite, and of course the well-known ore deposits that represent the driving force for a lot of the work that's being done on the Bushvelds. Intruded into the Transvaal about 2.06 billion years ago. And here is a good question about the size. So this is going to depend on whether you think the Bushveld represents separate, unconnected intrusions, or whether it's actually continuous. Now, everybody will know that in the western side, all of the layered cumulates dip to the east, and vice versa on the eastern side. And so you could think of the Bushveld as a single saucer-shaped lopolith intrusion or something like that. And so what are the constraints about that? Well, my lifelong partner, Sue Webb, a number of years ago, became aware that there's a kimberlite pipe right in the middle. So it's right under the H here in Bushveld somewhere. It's called Palnichat. It's a diamondiferous kimberlite. And she had the idea that if the Bushveld was continuous, then there might be some pieces of Bushveld cumulate rocks that the kimberlite, which is Cretaceous in age, has brought to the surface. And sure enough, when we went to the mine dumps, we found some little pieces of critical zone lithologies, so chromite-bearing pyroxenites, and this represents strong support for a connected Bushveld. It's also consistent with the gravity modeling, and also with the seismic data that are available in this part of the world. And they all point to the idea that the Bushveld is a single, very large layered intrusion, which can be approximated by a circle of about 400 kilometers in diameter. So this gives you about 200,000 square kilometers based on all these pieces of evidence. And the volume is somewhere between 1 and 2 million, world's largest LMI. In terms of the source, no agreement, but a lot of people have proposed a SCLM source, including my friends Steve Richardson and Steve Shirey, without crustal contamination. I don't think this is the case, but let's look at the evidence for what I'm about to show you. Okay, the Kondo lip is probably the least well-known of the 4 occurrences in Southern Africa, but I assure you that it represents a very important geological object. The age is about 1105, duration less than 3 million years, and so the Kondo is mainly sills, mainly dolerites. A few occurrences here and there of basaltic flows, but not very much. The basement is Proterozoic supercrustal sequences exposed in South Africa, in Zimbabwe, in Mozambique, and it extends actually into Antarctica. So the size in this sort of outline is about 2 million, but it might be a lot bigger than this because more recently there has been some Kondo material discovered in southern Angola, and that would substantially increase the volume. But if you don't want to include those, we can estimate a volume of about 2 million cubic kilometers. Once again, a lot of the work on Kondo, and as well as other lips, proposes an SCLM source, such as the work of Michiel de Kock, and there's other papers that suggest that as well. Okay, so the Karoo is really the big daddy of all 4 of these. It's huge, and it goes everywhere. So there's examples of Karoo certainly in Southern Africa, but also in Antarctica, in Australia, Tasmania, even parts of South America, such as the Falkland Islands. So this thing is a monster. The age is very well constrained, less than 1 million years duration. This is the work of a friend of mine called Henrik Svensson in Norway, and he determined a lot of uranium, lead, zircon, and baddelite ages by thermal ionization. And so these are very well constrained ages. I don't think we need to date this damn thing anymore. So the rock types for Karoo include basaltic flows. And on this map here, I guess I've distinguished flows in a lighter colored blue and the sills in a darker colored blue. So the flows, so there's very thick sequences of tholeiitic basaltic lavas in Lesotho, but also elsewhere. And in South Africa, mainly you have these sill complexes in the darker blue. So you really can see that they're everywhere. The size is at least 1 million. It may be a lot more. But we have to face the fact that a lot of the Karoo has been either eroded away. So there's no exposures here because of erosion. And there's also been some burial by younger materials. So we don't have a direct size of the Karoo, but we can infer that it must have been emplaced over a huge area in Southern Africa. The volume is somewhere between 2 and 3 million cubic. So this is a big one. Every source for the Karoo has been suggested, and this debate is still ongoing. So very prominent geochemists, Chris Hawksworth, our friend in the audience, Andy Duncan, Elam, and Keith Cox, all feel that that the best mantle source for Karoo is the subcontinental lithospheric mantle. But then there are other prominent people, excluding myself, but including Ian Campbell, Nick Arndt, who say that it could not have been the subcontinental lithosphere. And then there are lots of papers in which people sort of take an intermediate view, that you have combination of both. So here are the 4 Southern African lips mapped out on top of each other. And you can really see that they truly are spatially overlapping. So our friend Richard Ernst likes to see if he can figure out plume impingement sites. And so here is his suggestion for the 4 impingement sites of the different lips. There's Kondo, the blue one is the Karoo, the pink one is Ventersdorp, the green one is Bushveld. And what's interesting to me is that it looks like these plumes have been sort of dancing around Johannesburg for the past 2.5 billion years. And it's interesting because I'm sitting here in Johannesburg. It may be exciting to wait for the next one to start making itself known to give us the 5th large igneous province. That would be kind of fun, at least for a while. So what's interesting down here is if we can put any credibility into the volume estimates, and these are quite lousy because of erosion, because of poor exposure or burial. But if you accept those volumes at face value, you'll see that in fact, as a matter of time, the volume of the lips is increasing, which is very interesting and probably very important. Okay. So why won't it let me advance? There we go. All right, so let me go back one picture. So what you see here is that all 4 of these lips were emplaced or extruded into and onto the Cratonic entities in Southern Africa. So the Catfall Craton and the Zimbabwe Craton, which are linked by the Limpopo mobile belt, which represents the joining together by collisional events at about 2.7 billion years ago. So a lot of people talk about the combined Craton as either the Kalahari Craton or as the, I think Steve McCourt insists that we have to call this thing the Azanian Craton. I don't really care. So since the Craton has been proposed as a viable mantle source for these large igneous provinces, it's important to sort of figure out what do we really know about the Capfall or the Kalahari SCLM? And the answer is we know quite a lot. And the reason is because for about 100 years, people have been studying the mantle xenoliths that were thankfully delivered to us free of charge by kimberlite pipes. And so here's an example of one of the most abundant types of mantle xenoliths from the Cap-Vol SCLM. It's a garnet laerzolite. And of course, the kimberlites have also blessed us with their diamonds. And so it's really the inclusions in the diamond. So here's a beautiful garnet inclusion, but also there's pyroxenes and sulfides and so on, which if you're very clever and careful, you can use these inclusions to produce ages of the diamond forming events. And based on these kinds of studies, we know that the Cap-Vol or the Kalahari craton must be old, because the diamond ages range back to about 3.5 billion, with an average of about 2.7 billion. We know that the SCLM must be depleted based on the mineralogy and chemistry of the xenoliths, and also based on geophysical measurements. We know that it must be cold, and we can see this by looking at the heat flow measurements in the cratons versus other parts of the continental crust. And we know that it must be stable. So the Cap-Vol or the Kalahari must have been sitting there stable and happy for who knows how long, 3 billion at least. So old, depleted, cold, and stable. So this is an important property that we can use to think about whether or not it is capable of generating basalt. So starting in about 96, I think it was, and lasting for a 10-year period, there was the Cap-Vol Craton project, part of which included the Southern Africa seismic experiment. So David James and his friends from Carnegie put out a series of 50 or 60 broadband seismic stations and recorded for, I don't remember how long, 5 or 10 years, and produced a mantle tomographic image for the regions below the Cap-Vol and Zimbabwe cratons. So here is an example taken across the line from about Cape Town to about Mashvingo, and it goes to a depth of 1,000 kilometers. And what you see here is that the blue regions, which represent fast seismic velocity perturbation, they correspond very well with the boundaries of the cratons, both for the Cap-Vol and for the Zim. And the Limpopo belt you could probably include as a portion of the Cratonic entity. So we can use or estimate from pictures like this. We can estimate the shape and the depth of the Cratonic lithosphere, and if you do that, it allows you to compute a volume, and you can compute it in various ways. You can calculate the Cap-Vol or the Zim or both of them together, and the result is somewhere between 190 and 240 cubic kilometers. An interesting but unknown part of this picture is this red spot in the seismic tomographic image, which sits right under the Bushveld complex. And so we don't really know what the hell this thing is, but it probably is telling us something pretty important about the origin of the Bushveld. Okay, so what I've done here is I've tried to make some calculations about the effect of extracting large volumes of basalt on mantle sources from which they may have been derived. And so what I've done here is made a plot of source volume versus the result of taking a lot of basalt out of that source. So this on the y-axis is the increase in mg number that must have occurred if you take a lot of basalt out of a mantle source. So the yellow bars here are the Cap-Vol SCLM, or the combined Cap-Vol and Zimbabwe and Limpopo SCLM, which we can call the Kalahari. lip. So the input parameters to these kinds of calculations are the degree of melting, and I've assumed it's about 10%. You've got to know something about the source volume and the melt volume. You've got to know something about the source composition and the melt composition. And as far as these, I took an SCLM composition from Bill Griffin. He called it the Archon, which is meant to represent one of the most primitive types of SCLM. The melt composition I used was an average basalt from Lesotho. So it's a tholeiitic basalt composition. And you can see the results of these calculations. So if you have, so for example, Bushveld, which is about 1.5 million cubic kilometers. So if you take 1.5 million cubic kilometers out of the Capval SCLM, it's going to result in an increase in mg number of about 1 mg unit. And this is significant and substantial because a 1 unit increase in mg number decreases the density of the residue by an amount that's equivalent in temperature to an increase of about 200 degrees C. So this is the work of Tom Jordan from the 80s. Let me see if I can get rid of this thing here. Consequently, each time you take a million cubic kilometers or so of basalt out of an already depleted SCLM, the SCLM is therefore going to become colder, more buoyant, more refractory, with a higher solidus and less able to partially melt. So this is part of my my very strong feeling that the Capval SCLM could not have been capable of generating possibly not even 1, but certainly not 4 large igneous provinces that we know, that we can see on the surface. So a lot of people worried about this problem, thinking about it, who understand what I've just said, that that removal of large amounts of basalt from SCLM is going to have dramatic consequences on its composition and physical properties. So what these guys say is, well, why can't we have the SCLM be fertilized and refertilized over the course of time? And it is this enrichment by either fluids or by melts that that would be responsible for the geochemical and isotopic properties that you need in order to account for the large igneous provinces. Well, yes, I accept that that there must be some refertilization of the lithosphere, because we can see this in xenoliths, and it's represented by kimberlites and carbonatites, and so the SCLM certainly was refertilized. But if you want to refertilize the entire lithosphere by an enrichment event that would be sufficient to generate the large volume that you need for the large igneous province, this is going to wind up destroying the lithosphere, because necessarily you're putting back basaltic compositions, probably in the form of eclogite, into the SCLM in a widespread way, and that is going to serve to render the lithosphere as unstable. It's going to sink. It will founder, and we know that didn't happen in southern Africa because the Craton has been there forever. But there are a few examples of Cratonic lithosphere that has been destroyed in this way. So, for example, the Wyoming Craton in the US and the North China Craton, these are both examples of subcontinental lithospheric mantle that has been destroyed by this kind of refertilization process. Okay, another aspect that I considered is what diamonds can tell us about this issue. And so let's see if I can get my pointer working. So here on the bottom left is a PT diagram with depth or pressure going down and temperature going across. And I've plotted here the geotherms that are based on the heat flow measurements for the cap fall. And so there's a range of possible geotherms. And I've also plotted the diamond stability field. So diamond to graphite transition is this red line. And what it says is that if you're going to take the mantle lithosphere and heat it up to the peridotite solidus so that you start generating a large amount of basalt, what you're going to wind up doing by heating is destroy the diamonds in this region. So you destroy them by transforming them into graphite, except that below a depth of about 190 kilometers, those diamonds would be preserved. But more importantly, if we consider the oxygen fugacity, so heating up the lithosphere to the peridotite solidus is going to wind up oxidizing that lithosphere such that all of the diamonds would be destroyed by the reaction of, what is it, olivine plus diamond equals OPX plus magnesium carbonate. So here on this picture, the green dots are measurements of intrinsic oxygen fugacity from mantle xenoliths. And you can see that an increase of about 3 log units of oxygen fugacity is really going to kill all of the diamonds. So we know that this didn't happen because the diamonds are still present. Okay, so based on this thinking, you could ask yourself the question, where did this idea come from that the SCLM might represent an important source for continental lips? And the answer, unfortunately, comes from my geochemist colleagues, and I consider myself a geochemist, so if you like, I'm partly to blame for this. But it could come from the fact that continental flood basalts, which are shown by this pink banana-shaped thing, are more enriched isotopically in terms of neodymium and strontium isotopes compared to ocean island basalts like Hawaii or, I don't know, Reunion. And so this enrichment could maybe intuitively lead you toward a conclusion that continental flood basalts are different from oceanic ones because they were derived from an enriched lithosphere. Well, it's possible, but not completely on this basis, because there's quite a large region of isotopic compositions that don't correspond to the Cratonic mantle xenolith array, which is shown in this yellow blob. And so some of them do correspond, a lot of them don't. But what is often ignored here is that the continental crust, which shows an enormous variation in isotopic composition, really should be considered as a contributing factor in explaining the enriched character of continental basalts. So, so with that in mind, I wanted to look at the isotopic compositions of the 4 Southern African lips. And so here I've plotted age versus epsilon neodymium for the 4 lips: Karoo, Kondo, Bushveld, and Ventersdorp. So this is quite an old slide. I haven't updated it, but the data for Karoo is enormous, amazing amount of isotopic measurements have been made and continue to be made for Karoo. So now it's up to, I think, 650. But what you see for Karoo is an amazing variation in epsilon values of about 30 units spread between about +10 and about -20. Much less for the other 3 lips, but part of this might be due to the fact that we have far fewer analyses of these three older lips. And we're trying to do something about that now by making more measurements. But, you know, one obvious question is, what the hell is going on here with Karoo? How can you have 30 epsilon units spread in epsilon values? So is that telling you that this is the variability in heterogeneous mantle source, or is there a crustal component going on here? And so in considering the Karoo, I wanted to look at the Karoo holistically as a, you know, as an entire geochemical object. And so what I've been doing for the past several years is compiling a database of Karoo geochemical data and isotopic data. And so at this time, it was about 7,000. Now I think it's up to almost 8,000 individual rock analyses, which is a very ambitious effort by a very large number of people. What you see from this picture, so this is a total silica alkali diagram. Silica versus total alkalis. And what you see here is that the vast majority of magmatic products in the Karoo plots in this little white box here. So these are all of the tholeiitic lavas and a lot of the tholeiitic dolerites that have been designated initially by Keith Cox in the 1960s. So this is the low titanium suite of geochemical compositions in the Karoo. And the rest of this, aside from the dacitites and rhyolites, which are crustal, so the rest of this diversity is the high titanium suite of rocks. And I have to make the point that this high titanium group of rocks has really been oversampled and overanalyzed in relation to its volume. So I estimate that the main huge volume, either 80 or 90% by volume of the Karoo, plots in this little white box, and the rest of it is the high titanium suite, which occurs very restricted area that I'll show you in a minute or so. And I would argue that that this part of the Karoo has been overanalyzed, oversampled, but there's a very good reason for this. I mean, they're interesting. Who, except for maybe Goonie Marsh, would want to analyze hundreds and hundreds of tholeiitic lavas and dolerites, and they're all going to be the same? What does that tell you? Well, I want to thank him for doing that, because it tells you something very important, I think. Okay, so here is the isotope compositions for the Karoo mafic rocks, and you see a large scatter here. But what is apparent to me is that there is a suggestion of an array, a curved array, which looks to me like it might represent a AFC array, assimilation fractional crystallization array. And in fact, this is where all of the low titanium, the high volume low titanium suite rocks plot. So what I did was to try to do an AFC model, a quantitative one, starting with a parental basalt that isn't too far away from ocean island basalts. And then this array here that I've identified can be nicely matched by crustal contamination using a component that represents 1.1 billion year old granites. So here we're talking about the Namaqua Natal belt granitoids like the Concordia granite and so on. So you make a very nice argument here for assimilation and fractional crystallization of continental crust. Less than 9% of that would be needed. So if you want to consider a much older contaminant, such as Archean rocks of the Joburg Dome or something like that, you would produce an array that's down here. And this could be part of the explanation for the scattering of high titanium basaltic magmas for the Karoo, but I don't think so. I don't think that I see a nice coherent array here. But more importantly, these high titanium lavas and sills are really so super enriched in incompatible trace elements that many of them have concentrations of, I don't know what, strontium, rubidium, potassium, barium, zirconium, uranium, and thorium. The concentrations of those in the high titanium mafic rocks are higher than continental crust, and so that isn't really going to work as a contaminant component. So here's the same picture again, and this time I've chosen to identify the high titanium rocks in larger symbols. So anything over 2% TiO2, that's the normal cutoff, is shown here as a large symbol. And what I see is a very irregular looking array of minor SCLM magmas, the high titanium suite, which are, as I said, oversampled and restricted to a certain part of Southern Africa and also in Antarctica. So here, speaking more about the distinction between high and low titanium suites, the normal cutoff is about 2 weight percent. In the case of, so this is versus Mg number. And what I see here is the low titanium suite. So this is probably the AFC array that is indicated isotopically. And so the cutoff probably would be better defined as a sloping line in about this neighborhood, but it doesn't really make any difference. So, so this is really the idea by Keith Cox that was first applied to Karoo and successfully applied to lots and lots of other large igneous provinces. And this interpretation of the difference is, of course, related to different sources for the two different suites. So here you see a trace element. So I've chosen strontium to show you that that this probably oversampled set of high titanium suites, some of them are so enriched in strontium. You know, I became interested in why the hell it would be that a pickrite, so all these green dots are picrites. How can you have a pickrite, which is an olivine-rich rock, how could it be enriched in strontium to a level of about 1500 ppm? And so, so what I did is I took a few of these picrites, and I got my friends like Chris Harris and Guni March to give me some samples of these. And I looked at them in great detail. And I found that, you know, the idea that these picrites in the Karoo represent primitive melts is just not true at all. So when you look in detail at these picrites, what you see is that, number one, they're not melts because they've suffered some olivine accumulation. You can see that as phenocrysts. But more importantly, the rocks are extremely evolved. So they contain glasses and ground masses that are extremely evolved. So we're talking about glasses with trachyte or phonolite compositions. And this is anything but representing a primitive melt. So here is the picture where I've taken Google and input the Karoo data. And you can see what I've tried to do here is use a blue dot for low titanium and a red one for high. And it looks like the high titanium suites are really restricted to the arms of 3 belts of dike swarms and linear belts of lavas. And this is the basis upon which Ernst estimated the position of the Plume impingement source. So you see it in the same for strontium. I've plotted strontium, so the high strontium ones are in red. And once again, you see that it's pretty much restricted to a small area in the, what do they call it? The Lebombo and the Sabi and the Tuli arms of this triple junction. It's expressed on a map. So there is the Plume impingement source. You can see that it also extends a bit into western Dronning Maudland of Antarctica when you reconstruct it. And it may be interesting to correlate some of these very enriched picrites and and other kinds of rocks with carbonatite occurrences. So this is the work of Jock Harmer, who identified and dated and studied the carbonatites of Zimbabwe. They're the same age as the Karoo, and we may think of these as some kind of way to connect this kind of magmatism together. Okay, so I'm winding down the talk here. So I've placed the Karoo isotope data in the background, and I have plotted in the foreground the results for the minuscule results for the Kondo and Bushveld. And it's really pathetic that for the largest layered mafic intrusion on Earth with the largest repository of magmatic ore deposits, only 25 samples have been measured for combined strontium and neodymium. Kondo, similarly, was only about 15 samples. And at the time I made this picture, there was nothing, absolutely nothing for Ventersdorp. So we're trying to do something about that now. And at the present, we have, for Kondo, we've added another 60 samples, and also for Ventersdorp, but I won't tell you about that. I'll save it for next week when Kulikani is going to give you his results for isotopes from the Ventersdorp. And maybe someday in the future, Ben Hayes will talk about our work on the Kondo. But what you see here is a sort of a sub-horizontal array that you might be able to convince yourself is similar to the AFC array that we see for Bushveld. Okay, so here's the last slide, a summary. In my mind, these constraints and this thinking here shows that the SCLM is not a viable source for the large volume of continental flood basalt magmas. So this is the low TI suite. I consider a Plume source likely because of several factors, the correspondence of the most primitive magmas with ocean island basalts, things like that. I will admit, however, that I think the SCLM does melt sometimes during lip formation, and this I think is telling us that the high titanium, very super trace element enriched magmas come from a small amount of melting of enriched domains in the lithosphere. Okay, so another conclusion, if I'm right, is that the emplacement of melts from below the SCLM must imply that the melts ascended in very narrow channels, because otherwise it would wind up killing the diamonds in various places. Clearly that did not happen, and so there must be minimal interaction with the lithosphere, except that in some cases you can produce high titanium suites by melting these little components in the lithosphere. Of course, the magmas must come through the continental crust, and I insist that in most cases you've got crustal melting and assimilation going on before the magmas are finally erupted on the surface. Okay, so clearly we need more isotope data. We're trying to do that with my students and colleagues at WITS, and we'll keep you posted on the results. Now, I put this Martin thing here, rest in peace Martin, to remind me that all of this work that I've described in the talk today is published in a couple of months ago in the South African Journal of Geology, special volume in tribute of Martin and his remarkable lifetime. And so if you're interested in having a copy, send me an email and I will reply to you with a PDF file. Okay, that's the end, folks. Over back to you guys.
Hi, Lou. Thanks. It was very, very elucidating, lots of information, and well done. And I'm sure there's plenty of questions. And who wants to kick off? You might have just have a look. Chris Hatton raised the point about your volumes and that correlation you talked about, Lou. Is it actually real if you consider that there's probably more erosion the older units like the Ventersdorp, just given the fact that they've had much longer tour road.
Yeah, sure. The volumes that I've kind of tried to suggest are minimum volumes. They could be a lot bigger because we don't really know the full extent of where these lavas went to and where the dikes intruded. But what we've tried to do, what most people do, is make a map of the exposures of, let's say, basalts and dolerites, and then draw a boundary around it. So it's an approximation. I don't think they could be smaller than the suggestions that I made.
So we agree on that, and that's why we use the famous Kimberley Big Hole to show a section of Ventersdorp. As Gerard knows, some of the best sections of Ventersdorp were actually in our diamond mines.
I was wondering why you advertised my talk with a picture of the big hole, but now it makes sense.
Yeah. Okay.
Can you see Gerard Menkes' text on the side there? It says, note that we at Cornell et al. Published an age for the Makwasi, Ventersdorp at 2.72 on zircons from the sampling of the extrusive rocks from a wide number of widespread Makwasi occurrences with similar dates.
Yep. I think it would be very valuable for you to publish that stuff, and we clearly need more. What we really don't know is the beginning of the age of the beginning, the onset of the Ventersdorp. So, it would be a miracle if we could find a zircon in the komatiitic rocks of the western area. I don't think anybody has tried, and probably it's a good reason, because it ain't going to be there. But we really do need an age for the beginning of this magnetism. I don't know how to get it.
Lou, if I can comment there?
Yeah.
It's Gerard here. Lou, we did publish that paper in 2017 already on the 272 age. And also, we tried to publish an update with more dates on the Goed Genoeg and so on. It was turned down because it doesn't gel well with the dike work, but we're working on it. And also recently we published 2020, I think, published with Cornell, Dave Cornell, all of this work with Dave Cornell. We published updated dates on the VCR conglomerates, which give a tighter age for minimum or maximum age for the Ventersdorp. So it makes quite interesting reading.
Let me know how I can help you. I totally support you, and we need to get a lot more ages for Ventersdorp.
Thank you, Lou.
Lou, Warren Miller wants to know what makes you say that the Bushveld is the largest in the solar system.
Okay, let me qualify that. It's the largest one that we know of. I'm sure there's going to be bigger ones. So, for example, on Mars, there's a volcano called Olympus Mons that if you placed it with one end on Cape Town and the other edge will be almost to Joburg. It's about 800 or 900 kilometers in diameter. And such a huge volcano is going to have bushvelds under it, bigger ones even. And so it's the largest one to date that we know about. We're going to have to go to Mars and do some sampling and drilling before we can say these kind of statements for sure.
And Lou, coming back to the geochemistry and the isotopes, we mapped a whole series of gabbros down the west side of the Kruger National Park, and I think Theo Walraven did some subsequent work. Aren't there some, and I think they're about the same as the Macondo around that.
You're talking about the Timbavati, Timbavati stills. Those are really important because they represent fractionation. So you see some crystal settling and some evolution of the melts there. Most of the Kondo is all about the same. It's just a uniform dolerite. Doesn't change very much. But they're nice and fresh. Yeah. They're nice and fresh, and we have analyzed some of them, and they seem to point to very primitive composition. So no crustal contamination, or very little.
Okay, so you've got that data.
Yeah, we do.
Okay.
Actually, Gumsley would be interested to know about dating on the dolerite sills in the Ventersdorp supergroup, particularly the Klip-Proversberg group, and combining it with geochemical studies. The problem is access good for drill core, and
I really don't know. Maybe Gerhard will know better than me, but most of the Ventersdorp is actually lavas, and I don't think there's much in the way of dolerite sills, but I could be wrong. If there are dolerite sills, yes, that would be a great target for dating.
Ashley, what is that map on the wall behind you?
It's Iceland.
So there was some lava flow you were hiding from us.
Oh, no. It's a map of Iceland, a geological map of Iceland.
Does that answer your question?
Yeah, it does. I mean, we've dated some sills in the Ventersdorp supergroup in Fredefort Dome. That was the 2.78 age which got. But you know, I know you know, we didn't actually get a direct age on the Klip-Proversberg group itself. We only made some inferences as to what the potential age is. However, you know, I've got a laboratory here set up. You know, I'm more than willing to do any more bedelite age dating on any particularly dolerite sills, dolerite dikes, which may be connected with the Klip-Proversberg in particular. I've been collaborating with Gerhard, and I'm now that I've got set up here, I'm going to try and do some age dating for him on some of the units there, which he has. So, but I'm interested in working with Lew as well. No problem.
Yeah, Ashley, I would love to help you. I to the extent that I can. You know, for Ventersdorp, almost all of our samples come from pieces of drill core or from powders that were taken from drill core. From students of Spike McCarthy, who seem to have repeatedly studied Ventersdorp rocks for a period of about 15 years. And so I don't know very much about the field exposure, field occurrences of possible dikes or even lavas that might be favorable to contain bedelite or zircon.
Yeah,
So
it's difficult, yeah.
And Ashley, where are you for interest?
Oh, I'm in Poland now.
And is that where your lab is?
Yeah, I got my separation. I still do my age dating in Stockholm, but I do all my separation here in Poland now. I have a facility for that. So, yeah.
Where are you from originally?
I was born in South Africa, in Johannesburg. How I ended up in Poland is a long question.
Right, we'll spare you the detail. Right, and Gerard, I mean, you would be the obvious guy to pick out samples for Ashley, or I mean, are the two of you talking?
Yes, yeah, we have them.
Yeah, John, we gave some samples to Ashley some years ago, and yeah, we're working on it. Hopefully, there's much more we can try apart from those samples, because that's the great mystery: is the mafic rocks, lavas of the Ventersdorp, like Klip-Proversberg and also Allenreich, especially the Allenreich is very intriguing on where does that fit in. And like I said in my talk last week, wonder if there isn't a felsic component of it as well.
Right, lots to do. And Lew, where does this project all go? What's next? I mean, you've obviously got a massive data. You've got a whole bunch of students. I mean, is this just the start of a bigger project to unravel the?
This start of this project is actually a huge undertaking. I was very dejected when I compiled all of the geochemistry and looked at 650 isotope analyses for Karoo and none for Ventersdorp. So what I did was I made an application for a grant to the, the Harry Oppenheimer Trust. And they were very generous. They granted me a big grant to, you know, what I promised in there was to produce 100 combined strontium, neodymium, and hafnium isotope measurements for each of the Ventersdorp, Bushveld and Kondo. And so we have begun with this. And so I have two PhD students. One is KK, which you will hear from next week, and his responsibility is the Ventersdorp. So he'll share with you, I think he has about 60 or so isotope analyses, and he'll tell you all about what he thinks this means. And then the other student is working on Bushveld. But Bushveld has been a bit difficult because what we really want is combined hafnium with strontium and neodymium. And it turns out that the Bushveld rocks are so low in hafnium that you really have to have special super high analytical capabilities. It couldn't be analyzed by the normal techniques, but so we haven't really started yet with the isotopes on Bushveld, but we've identified samples, and now that at Wits University the 2 new mass spectrometers are arriving, and combining that with the WIGGLE, the Wits Isotope Geochemistry Lab, in which we can do very, very high quality isotope dilution, we should be able to start getting hafnium as well as the other 2 for Bushveld. As far as Kondo, that is the job of our colleague Ben Hayes, who I think is on the call here today. So he is the one who's championing the field work and the analytical work and the isotope work on Kondo. And we have a paper almost ready to go on this one, and also on the western area formation of the Ventersdorp. So I'll keep you posted.
Okay. And
Yeah, I've got a question. Can I go ahead, John? It's Neil.
Yeah, go for it, Neil. How's it?
Lou, first of all, thank you very much. I learned a lot there. I enjoyed your talk immensely. It's a fairly simple question, perhaps, and that is you described the Ventersdorp as 2.7, lots of basalts, some ultramafics. Now, that's exactly the same as a greenstone belt so far in say, Western Australia. What are the similarities and differences with respect to all this difficulty sorting out origins?
So you're making a suggestion that Ventersdorp is kind of equivalent to what a greenstone belt would look like.
I'm saying with respect to the 2 main rock types and the age. Now, I know that's very simple, but with respect to those characteristics, that could be in Kalgoorlie, 2.7. And so
I'm going to ask you to tell us more about Fortescue, which I know very little, but a lot of people have connected it to that thing. But yeah, if you want to think of Ventersdorp as a greenstone belt, it's perfectly fine, except that the greenstone belts are much smaller. This goes over a huge areal extent. Greenstone belts are kind of, I don't know, most of them are slivers and affected by thrust emplacement into linear belts, but that just may be a technicality. If you want to think of Ventersdorp as a typical greenstone belt, I have no objection. Tell us more about Fortescue. Could that be a correlative of the Ventersdorp?
I'll come to that. That's more than a 30-second answer. Yes, it could be, because the age is the same and some of the rock types are the same, but I'm not concerned about the deformation and that makes greenstone belts look long and thin and all that stuff. It's just you've got to get a large amount of mafic rocks and some ultramafics onto the surface at 2.7, and you're doing it in Western Australia, South Africa and elsewhere.
Yeah.
Why isn't there a link, similarity?
Either that tells you that whatever tectonic setting or geodynamic setting you like for greenstone belts, could that apply to things like the Ventersdorp? Or
Yes.
Looking at it the other way, you could say that all the greenstone belts, Barberton and the ones in Australia, must have formed by some kind of plume activity. This will be the way to give you a large volume of basalts and piccrites and sometimes komatiites. So I think I would prefer to look at it the second way. Plumes are what controls large outpourings of lavas.
And I mean, just, you know, for the uninitiated and non-experts, and going back to Martin de Wit's work and your work, Lew, I mean, my very simple recollection is, you know, when you start talking about Barberton, it was oceanic crust.
Yeah.
You know, so
That's right.
there was no real sort of continental involvement. I mean, you know, in all of these lips that you're talking about, you can't get away from the continental aspect or involvement or crustal interaction.
No, that's right. But nevertheless, the driving force, the heating mechanism for even oceanic environments could be a plume, just like you have in Hawaii and Reunion and millions of other ones. So you know, that's the way I look at the Barberton, the very ancient greenstone belts, 3.6, 3.5 billion. You've got a lot of basalts and a little bit of komatiite, and you've got to have a heat source for that. Some people talk about subduction. I don't know. I think these are formed in the oceanic lithosphere by ocean island plumes.
Lew, I have a question about the bulk of the Karoo. That's the low titanium suite. And you made the point that it could be an AFC array, which I think is certainly possible. But the problem I've always had with that is, as you correctly pointed out, the bulk of the Karoo lavas are an incredibly small group in terms of composition, that white block of yours. Now, how do you reconcile a major AFC process with a good few percentage of AFC with an extraordinary consistency of composition?
Okay, well, a lot of the AFC array that you will have seen on the isotope diagram. So a lot of the enriched part of the array is actually andesitic, sort of basaltic andesites to andesites, and I didn't really include that in the that white box. The white box is based on Guni's. Let's say I think he had something like 400 or something analyses of Lesotho flows, lava flows, and they were so uniform that it just induced me into making the point that these are very, very uniform things. So I didn't include the andesitic rocks on the white box. Maybe I should have, but the point is still going to be the same.
You there, Lew?
I'm here.
Oh, okay, so you finished. Andy?
Totally finished.
Okay.
No, just as Lew's made the same point. It's an issue if you're going to have major crustal contamination. It's difficult to produce an extraordinarily consistent composition over a large area and that block of time.
Yep, I agree. Most of the compositions are going to be homogeneous because it's not a major amount of crustal contamination. It's pretty small. It's actually less than 10%. So you're still going to retain your volumetric proportions and the homogeneity of basalt in that story.
And something like the Bushveld, I mean, have you been able to go back and sort of, it's the million-dollar question, recalculate the original magma composition? And, you know, we obviously see all that fractionation and settling. And,
you know, I've often said that what you just suggested is going to be impossible now and forever, because the Bushveld is entirely cumulate rocks. And, you know, there's been so many attempts to define parent magmas, parent melts, by using all kinds of different backward modeling or using sills and dikes of chilled compositions and so on. I think it's all crap. I really don't think we know what the parental magmas looked like for the Bushveld. We don't know how many there are. But this is part of the dispute, you know. If you listen to other people, you will hear great confidence in their assertions that no, the bulk composition or the parental composition for the critical zone must be this or that. I'm just not sure, and I don't like to play this kind of a risky game. You can get into a lot of trouble.
Okay, so your best, most primitive or sort of original magma is represented by the very consistent Goonie Marsh basalts. Is that what we're saying?
Yeah, basalt is the most common rock type on the surfaces of the terrestrial planets, including the Earth. And basalt has got to be an important melt or magma composition that I think gives rise to anytime you see a mafic rock, we're talking about basalt. Occasionally it's something else, komatiitic or basanitic or lamproite or something like, but basalt is really the big player here. And so if you ask me what I think the parents of the Bushveld, they're basaltic, at least broadly defined. I wouldn't want to give much detail to tell you what the titanium content or the hafnium content of the primary melt for Bushveld. That's just foolishness.
Okay. And just going back to the Deccan, although you haven't been there, Lou, you've obviously seen it. If you go and look at that, and there's a lot of data there as well, but if you go and look at that composition, is it also that very consistent sort of tholeiitic basalt?
Yeah, it is. It's Keith Cox. Now, wasn't Keith Cox your PhD supervisor?
Yeah, he was involved with Andy and a few others, Tony Erlang, yeah.
I mean, he is brilliant, that guy. He was the first to identify the two types of suites of magmatic products in the Karoo, the high and low titanium. Yeah. And that has been discovered in just about every other large igneous province that you can think of. So Deccan, Paraná, Etendeka, the Siberian traps, the camp plume of North America and actually Africa, but pretty much all of them show this this relationship of large volumes of tholeiites, low titanium, and then much smaller and geographically restricted suites of higher titanium, very enriched compositions sometimes. And we all have our different theories for why this is. My explanation is that the low titanium, high volume stuff comes from the Plume source, sublithospheric, and the high titanium, very minor and geographically restricted, comes from zones in the lithosphere that are enriched by usually some unknown process.
And to be honest, they're much prettier, more interesting rocks compared to your boring old basalts.
I know, I agree with you, but don't you think we owe credit to Goonie for being so persistent in such a boring rock, analyzing it over and over? He must have 1,000 analyses of rocks that are almost the same. He wouldn't stop.
No, absolutely. Right, Gillian's made a point there. Gillian, do you want to explain your comment about plotting that array?
Which array?
Maybe looked at her on the chat box.
Everybody, I enjoyed your talk immensely, Lew.
Thank you so much.
I just plotted the volume that you gave for the lips versus time, and they all fall in a straight line, more or less.
Oh, you mean increasing a volume as they get younger?
Yes.
Yeah, it's amazing. We know, of course, we know the age quite precisely compared to the volumes, which are just a crude estimate. But that, to me, that says something very important, because if it's true, then how can you appeal to the lithosphere as being a viable source for these things? You deplete the lithosphere each time you take basalt out of it, and if you're increasing the volume in a mantle source that is increasingly becoming more and more depleted, then this borders on the impossible. But thank you for making that plot.
Okay, last couple of questions. Any parting shots?
We've got one from Hendrik Smith that said, is that not a bias of how much is preserved?
Yeah, it is. Of course, it might be exactly that. So the
Well,
older ones, like Ventersdorp, are, you know, the uncertainty in the volume estimate is much higher. So, you know, I don't put much credibility to estimating the volumes with very much confidence and precision. So you could be exactly right.
Right. Any final questions?
Yeah, if I may throw one at Lew, it probably displays my ignorance more than anything else. No mention of the Great Dyke. I mean, is that not a lip?
I don't think it's big enough. I don't know.
Okay.
I don't think it's big enough. But I must say that I have never calculated the volume of the thing. I don't think it's going to qualify.
Yeah, but is the size really that critical if we're talking about source material and magma, etc.?
Well, if we're talking about lips, the first word in that acronym is large.
Okay.
So that's how they're defined. And I'm not sure that, you know, on the table next to me, I have Richard Ernst's book. And I don't think he has the Great Dyke in there as you know, as one of his lips. He does in that book, which is really quite a very good book. It's a compendium of all of the lips that are present not only on Earth, but in the solar system. So there's 200 terrestrial lips, and I don't think that the Great Dyke is included as one of them, but I could be wrong.
To be honest, Lew, yeah, I think it probably is, but Richard is a bit too liberal with what he classifies as a lip. He likes to make every dike a lip sometimes.
I know exactly what you're talking about, and I have criticized him for this. You know, so for example, in Africa, he took the Kunini complex, which he thinks he knows the age, but let's say he does, and then he found a rock with a similar age. Where the hell was it? I don't remember. In the Sudan. And then he said, well, it's a large igneous province. You connect those two and you've got a lip. But that's just completely garbage. The Kunini complex is not a lip. It's a massif type anorthosite. And so, you know, he loves to see lips everywhere. And I like the guy anyway.
Yeah, he's got the Great Dyke in. I just checked. But he's got lots of things in there. But by the way, what about the 1.9 event, 1.9, 1.88? Because that's in both Karpval and Zimbabwe, the Mashonaland sills, for example.
I don't know about it. I don't know how big it is. I really don't know very much about it. There could be others. You know, I said there's a minimum of 4 in Southern Africa. There could be others. The Dominion is another example. I don't know much about Dominion. I've decided to pick the 4 biggest ones, and why don't you write that up as being a 5th one?
I think Richard beat me.
Richard
Ernst.
Oh, okay.
Julian says that the lower lip bound is a bit arbitrary. Agree?
You mean the size?
Yeah, other people have suggested using 50,000, for example.
Wow. It's pretty small.
I don't think it falls into 2 groups at all. You can find areas with 99,000 or...
Again, it depends on erosion and preservation and burial and...
Yeah, but I mean, you can't get away from that volume, Lew. And I mean, you talk about the Bushveld, and you haven't talked about all the very extensive soils that you see out in the Eastern Transvaal and
absolutely
and places like that too. I mean, you know, the Bushveld is actually a much bigger animal, and I think that's, you know, as you say, the hallmark of these amazing, you know, large igneous provinces. They're just huge, and they just keep going on and on.
I say that we don't really know the size of the Bushveld, which is true. but it seems to be getting bigger and bigger every year as people are discovering new parts of it. Like, you remember the northern limb? Well, geophysics has shown that it goes way to the west. And so you can increase the volume of Bushveld by about 80,000 cubic by including that thing. And who knows where else it goes. Malopo Farms is another possible correlative. Then there's the Trompsburg down in your neighborhood. Yeah, Bushveld is a serious monster of an event.
Okay, well, great. Thanks for your contribution, Lew, and we want more of you. I mean, we've got to keep up the sort of David Ashwal, group and stirring the pot and throwing out new ideas. We need it, and also great to see you guys bringing youngsters through as well. That's fantastic.
Yep.
So
Okay.
we really look forward to hearing from the younger scientists in the weeks to come.